So today we are talking about unlocking efficiency, tackling real-life production challenges with simulation and OLP. And this time we are covering both of our product families. So my name is Ekaterina Berdasheva. I am a marketing specialist here at Visual Components, and I will be your host today. Visual Components is an international company, initially founded in Finland, and we are headquartered here in Espoo. But we also have offices in Tampere, another Finnish city. Actually, our robotics office is located there. Most of our robotics colleagues are there. And then we also have two offices abroad. So one in United States of America, in Indiana, and also in Munich, in Germany. Then also we have a global partner network, so over 60 partners across the globe. You can find us in almost every continent. And at the time, we are 128 employees and growing. So at Visual Components, we build world-class 3D manufacturing simulation software. And also we extended our offering in 2023 to include industry leading robot offline programming software. So the software that used to be under the name Delphi Robotics is now called VC Robotics OLP and is part of our product family. Proud to say that today our solutions are trusted by more than over 2,400 organizations in the manufacturing industry worldwide, starting from small local manufacturers and system integrators to large global corporations. And in today's webinar, we are going to hear from two of our internal experts. So I will, with this, give the floor to my colleague Mikael and Jyri.
We're excited to see so many of you here taking time out of your busy days to learn a bit about this topic. Today's topic is, as the title says, unlocking efficiency, so tackling real-life production challenges with simulation and robot offline programming, so OLP for short. Your webinar presenters for today is myself. So my name is Mikael Saksi, and I'm an application engineer here at Visual Components since 2022. As an application engineer, we do anything from customer consultancy with their layouts, technical support for sales. We gather specs for our software, we train customers, and so on. Myself, I'm in the factory simulation team, so that's my focus area. And last year, I did my thesis research for Visual Components on the topic of how we should develop our software for production managers. Outside of work, I'm a sports enthusiast, so I can do whatever sport the season allows, whether that be paddle, swimming, weightlifting, and so on. And then we're, of course, joined by our colleague Jyri here. Would you like to say a few words about yourself, Jyri?
Yes. Welcome to the webinar also on my behalf. I'm Jyri Luhtio, and I'm working as a sales manager for the offline programming software here at Visual Components. Basically, what my job is that I'm trying to help our existing customers and also potential new customers to get a little bit more out of their robotic stations. Doesn't matter if it's a welding process or painting or cutting. Trying to get a little bit more juice out of the robotic investment that they have made. So I have a background from welding and production automation. I used to work in that industry for 10 years, and now it's nice to share that knowledge to the customers and try to help them achieve more with their robotic investments and robotic stations. Outside of office hours, I tend to like to spend my time with my family and with my kids.
Sounds nice. Okay, so the outline for this presentation is as follows. First, we'll start with the challenges faced in production, the challenges that we think our customers and also our potential customers face. Then we'll look at kind of what is factory simulation and OLP from a very basic level to get everybody on board. How are they connected? what are the benefits, and from there we move on to some customer cases where you see real use cases, real benefits that these customers got from their projects. But before we get to the actual matter on hand, I have a question for you, which is, what do you think is the estimated industrial robotics market value by 2032? Currently, we're standing around $18 billion in 2024. So we have three options here, A, B, or C. And you should see a poll come up.
Yeah, and I can give a hint. It's gonna be quite dramatic increase in the value. So I can help you a little bit.
So assume that most of you have answered the poll. So I cannot see the answers myself, but I'm guessing based on Jyri's hint, most of you guys got it. So the market value is estimated to exceed $45 billion. So what that means in the next 8 to 10 years, the market value will almost triple. What does this mean and how is this relevant in our presentation? Well, the more robots are being installed in the next years, it means that we'll need tools like OLP to program these robots. And also we will need simulation to simulate these new robot cells. So what this means is the prevalence and presence of visual components will only, or the simulation software will only increase in the next kind of 8 to 10 years. Okay, then moving on. So what are the challenges faced in production today? Well, the first category that we have is process and equipment issues. And these are things that Jyri and I have seen through research, from talking with customers and actually visiting real production facilities as well. And what we mean by process and equipment issues is, for example, unexpected machine breakdowns. So perhaps you have a lathe in your production facility and there's a mechanical component inside this lathe that wears down unexpectedly, causing the machine to stop, and potentially also causing a disruption in the whole production line. Then we might have quality issues. So perhaps a machine is not producing to spec, it's producing outside of spec, which is causing scrap components as output. Then we might also have issues with space and equipment constraints. So perhaps we need to introduce new capacity, a new machine to our factory, but we have to optimize every single square meter of that factory to fit that machine inside. Then we have another category, personal issues. So we might have unexpected personal illnesses. So perhaps a larger group inside the factory personnel has gotten some illness or some flu, or a pandemic like Corona also, of course, caused a lot of absences inside our factories. Then we might have unmotivated workers. So perhaps they're not sticking to the cycle time that allows us to produce the production output we need, or they're not following the guidelines or the process specs per instructions. So maybe they're not respecting all the safety rules, for example. And of course, really relevant to this robotics stat I showed earlier is finding suitable workforce. So we need workforce that are able to operate complicated equipment, such as robots. So we need people who are able to program, maintain, and fix these robots as well. And if we take a step back, we might also face some operational issues. So, for example, we might have an inaccurate demand forecast. So let's say there's a seasonal change in the product's demand, and this will cause us to have to ramp up production very fast to meet this demand, causing all sorts of kind of reactiveness on our production plan on our shop floor. Then the other side of the factory, the raw material. So we might also have issues here. So we're not able to get the components of the raw material to our factory, and recent events such as the blockage of the Suez Canal is a great example of what this does to our supply chains, or pandemics like COVID-19, of course, as well, caused a lot of global supply chain disruptions. And then last example here is unrealistic demands set by management. So perhaps the demand or the demand set by management is really stringent or almost unrealistic to achieve. So we have to uphold almost impossible factory uphold times and so forth.
Yeah, I think if we think about the personal and operational issues, those, let's say, during the COVID times, those were quite remarkable changes what companies faced. And then if we think about in the long term, this, let's say, finding suitable workforce, I think that's going to be a challenge in every industry, because, let's say, from the welding point of view, I know that there will be a huge lack of, let's say, skilled welders in the, let's say, coming 5 to 10 years. and you typically in that situation companies are facing the let's say issue that they need to invest in automation, and typically it means robotic welding station, and of course trying to get maximum output from that. It means that you need to have a suitable software also to use it.
Precisely, yeah. Of course, these issues we've highlighted are all the issues. These are a snapshot of all the issues, and therefore we'd like to hear from you as well. So what production issues do you face? Or if you're in a production organization, what do you think are the most sort of on-topic issues that production organizations face today? And Katja, are you able to see the poll results?
Yes, so the first option, process and equipment issues, 41%, so that's the leading one. Then personal issues second, and operational last.
Okay, good. All right, then that is from our point of view a very good result, because I believe factory simulation OLP can either solve or at least address a lot of the issues in this process and equipment category. So let's go on then to the next question, which is what is factory simulation? I'm sure a lot of you already have a good idea of what this is, but to bring everybody to the same understanding, what is factory simulation is perhaps best explained through this video. This is a screen capture of Visual Components. And what we do in factory simulation first is we start with building the layout. So we drag and drop components, readily available components from our e-catalog. But we have over 3,000 different components available to the customer. We have over 70 different brands, over 1,800 different robots. And here you can see we're building a very simple robot cell, testing out different robots and so on. So we're building this concept. And from there, after we've built the robot cell, we can start adding the buffers, the inventories. We can add the manual workstation, our AGVs, our human workers, and so on. And now we've got some kind of layout concept ready. From there, we might want to do a feasibility study. So we want to start looking at the numbers. Can our robot cell achieve the production output we need it to achieve? Is the robot utilization high enough for us to achieve this production output? Here you can see we're looking at some statistics to validate these questions. From there, we can also look at, for example, AGVs. So do our AGVs move enough components and material around the factory so that we can achieve the right production output? Of course, there's a lot of different KPIs that you can look at. This is examples of some. A nice framework, how I like to explain how simulation looks from a theoretical point of view, is we have a simulation user who builds this digital production system that you saw earlier in the video. From there, they get the output data. So this can be statistics in the form of these dashboards that you saw, or it can be also visual insights that you get from this 3D world. From this, the simulation user uses this as feedback to make further alterations to the production system. So for example, let's add another AGV, let's move the location of the robot cell, so forth. From this iterative process, the simulation user then takes this insight into the real system. So this is what the factory simulation looks, but what about then the side of OLP? Perhaps, Jyri, you could also enlighten us with this, right?
Yep. So if we think about in a nutshell, what is robot offline programming? So typically, let's say it means that you are doing the programs for the robot with the computer. And typically, companies, they can also do the programming for the robot with the teach pendant, but then it means that you are physically at the station using the teach pendant and basically taking away the productive time of the robot. But then if we go to the offline programming, you can do the same programming on the PC while the robot is still working and basically doing the thing, doing the productive work that it is designed for and bought for. But then let's say on the right hand side, you can see that the typical way of using the offline programming is only use it for the production purposes. But then if we think about in a little bit wider spectrum, so using it also together with, let's say, design department. So using the offline programming tools to create more, let's say, optimized designs for the fixtures and also more optimized designs for the products. So that basically then allows the automated systems to work more on the products, so that you can also increase the production output. But that's typically it's only used for the production, but I emphasize that basically working or using the offline programming tool for more cooperating with the design department and also with the manufacturing department.
Yeah, exactly. And there is a connection between factory simulation and OLP, right, Jyri?
Yeah.
Yes, which we can look at in the next slide. So the next question is, how are factory simulation OLP connected, so offline programming? And the way we like to explain this is using this framework, which we show to customers to really showcase the capability of Visual Components. Here at the top left is the very conceptual stage. So this is designing concepts. This is, if you will, starting from kind of a flipboard, a sketch. You have really no idea how the end result looks, but you want to come up with some ideas. And then towards the end of this workflow here, we have the real commission system. So we go from concept to reality. And if we look more closely, factory simulation is the first two stages. So it's the layout design that I showed you earlier. So we generate a couple different alternative layout proposals. And once we're happy with one of these proposals, then we start to do a feasibility study. So this includes some analysis of our proposed system. We look at, does the system satisfy the requirements we've set? Does it produce enough output that we want? Is the robot utilization what we want? And so forth. There we move a bit closer to the real commission system. So what we do next is we can validate the control logics and robot programs. So this is this third black box here in this line. And what this means is that, for example, let's say you have PLCs in real life. You can validate the logic of these PLCs by connecting it to our software and testing the logic in a virtual system, a virtual simulation. From there, we move closer to reality, so closer to actual commissioning, where we actually start looking at programming robots for real commissioning via the OLP tool. And perhaps, Jyri, you could say a few words about this.
Yeah, as you, Mikael, mentioned, that this basically describes quite well how those two worlds are connected to each other. Of course, typically simulation is used by some other, let's say, person in the company, and OLP, or offline programming, is used by another person, but there's a quite strong connection, especially on the software side, that you can use the software for many of these things. And then let's say at the virtual commissioning phase, then you are trying to, or let's say then you are basically working a little bit closer to the actual machines. But then when we go to the offline programming of robots, then you are basically tied to the actual production and actual machinery already.
Exactly, yeah. So from concept to reality in a nutshell.
Yep.
Okay, so that is the connection, and we've looked at a bit of factory simulation OLP separately. But what are the benefits of using simulation and OLP for improving production performance? Well, let's start from the side of factory simulation. The first kind of obvious, but also very generic benefit is process optimization. So this can, for example, be solving this classical line balancing issue. So if you're creating a new greenfield system, so a system that hasn't been commissioned yet, you might want to optimize the different process stages in your factory. For example, let's say you have a machining stage, and then after that, you have a quality inspection stage, and you want to balance the cycle time of these different processes to ensure a smooth throughput throughout the factory. Then what we also might want to look at is testing out what-if scenarios in a risk-free environment. So this is more for brownfield systems, factories that have already been built. And rather than taking the risk of testing out these changes in the real factory, you can do these changes in the simulation in a risk-free environment. So what if we moved, for example, machine to place X? How would that affect production? Or what if we change the logic of the warehouse sorting system? How would that affect production? Rather than having to take the risk of doing this in the real life production facility, we can do it in simulation. And of course, testing and validating your system for commissioning. So before you've actually built the system, you might want to look at things like, do the AGVs collide in the layout? Do we realize that a certain machine or robot is not actually able to reach the component? These are all kind of mistakes that we can avoid before actually commissioning the system. Then for the side of OLP, Jyri?
Yeah, if we think about the, let's say, biggest benefit typically, and what is easier to, or let's say easiest to realize, is the robot utilization. Just becoming from that reason that you are not taking away the productive time of the robot that you are doing if you are teaching with the pendant and doing the online programming or online teaching of the robots. So typically it means that we can do, let's say, the programming time between online teaching and offline programming. It's typically, we can say it's 5 to 10 times faster, but also the utilization rate of the robot can increase from, let's say, 10 to 15% up to, let's say, 80% even. So there's a huge difference compared to online teaching and offline programming. Then the next one, the repeatable quality and high quality. So companies might have like, let's say, 2 or 3 operators who are creating the programs for the robots, and they might have different ways of doing certain things on the products. So what is good in our software is that you can create like templates and libraries of how to do certain things in your products, and basically that enables you to always use the same optimized ways of creating welds or creating painting paths or creating cutting paths for the robot. And all of the operators, they can use the same optimized ways of doing things, so it creates high and repeatable quality. Then the last part, let's say, improving the product and jig design. I know I already mentioned that in the couple of previous slides, but basically that enables companies to achieve more with the robots that they are using. So creating, or let's say, making more automation level in the production. And of course, then you can predict how your production is working, or is there going to be a peak in the production flow or something like that. So if you can do more of the things with automation, it helps you in your production overall.
Yep. And you guys don't have to just take our word for it. We also have a couple customer case studies where we saw some concrete evidence and some examples of what the customer or what our previous customers have done. So some of their use cases and so forth. So from the side of factory simulation, we have an example from Güdel. So Güdel is a logistics kind of solutions provider, well known in the manufacturing industry, and a challenge they had was designing and delivering a system that delivers around 12,000 car tires per day. In addition, there was a complicated order intake for this system, so the tires needed to be just in time and just in sequence. What this means is that the car tire delivery was synced with the car orders, so the right tire had to come at the right time. Then there were, of course, numerous product types, so this also added complexity to the system. What was the solution? The solution was to create a visual components simulation. So what Güdel did is they utilized a large library of the readily available components in the ECAD, which I showed you in that video. And so, for example, they utilized all the straight conveyors, sorting conveyors, conveyor systems, and other logic that we have readily available. Then Güdel also had some of their own smart components with very specific and advanced logic. So they modeled these own smart components. These include, for example, Güdel linear axes, Güdel robots, and Güdel portals. From there, after they connected all the different components, put the logic together, then they started to analyze some of the KPIs, key performance indicators, using the built-in visual component statistics. From here, they looked at things like the cycle times of different cells, cycle times of the whole facility, portal and buffer utilizations. Benefits from this for them? Well, firstly was the verification of very challenging customer specs that we saw. And this is a quote from one of the project engineers. Part of this project is, thanks to the evaluation of cycle times and utilization of the portal bridges, we're able to ensure that the system meets the customer requirements in terms of throughput. The simulation also showed that the number of buffer spaces is sufficient. Moreover, the whole system was modeled in around three man-hour weeks. So the development time of the project was only a fraction of the time previously required, which also reduced the whole time of the delivery of this project. And then lastly, of course, it increased the customer's trust, as the customer was able to see the system builder's solution in this system, this complicated system before delivery. So they got the confidence that what they're delivering will also meet the specs. Then we have another example, and this example is a bit different to the previous example. So the previous example, we were building something new, but in this case, we have a brownfield system. And this company, part of this project, they already knew how the system works, so how the real factory works. And unfortunately, due to NDA, I'm not allowed to tell the company's name, but they are an Asian company from pharmaceutical industry. And this company had some very tangible and practical questions. So the questions they had is, how many technicians do we need? When should the inventories alarm the technicians to replenish the inventory? And how many bottles should the technicians fill per replenishment cycle? These were all kind of things that they wanted to find answers for without having to disturb the real system. Solution, again, was to create a visual component simulation based on the real life parameters. So what they did is they modeled this layout, they simulated this layout, the material flow, and so forth, visual components, then validated this system by comparing the KPIs to the real system. And from there, they started to play around with the different parameters. So how much does it affect production if we change the number of technicians? What about the replenishment rounds? And so on. Then they compared the various scenarios, and they compared particularly the buffer and production output statistics that you can see here at the bottom. Benefits for them. The main benefit for them, I would say, was that they got very clear answers to these questions. Regarding the first question, how many technicians do we need? They found that they need exactly 2 technicians to reach 95% of uptime, which was sufficient for them. They also found out that the inventory alarm has to go off when there's only 10 minutes sort of raw material left for 10 minutes of production, and that minimum 80 bottles need to be refilled every time the alarm goes off. In addition, other benefits for them was the very quick and easy setup time of this simulation due to the existing readily available VC components. And they were also able to visually observe how the behavior of the factory changed with these parameters due to the visualness of the simulation. So these two are kind of examples from the side of factory simulation, but what if the customer wanted to move or look at more of the OLP side? I think, Jyri, you have a couple of examples from this, right?
Yep, we can jump right to those. So this first example is a well-known provider of welding equipment, so Fronius from Austria. So typically they are very well known in the welding industry for their high-tech welding equipment. But then the challenge that Fronius was facing a couple of years ago was that they wanted to also provide full robotized solutions for their end customers, but they were lacking the software solution that can handle basically multiple phases in the let's say sales cycle, and also in the commissioning, and also regarding the offline programming. Then of course, if we think about robot stations, you can have a very simple station, or you can have a complex station with multiple robots, different kind of processes, handling, welding, cutting, jigless welding, and such things. So trying to realize those kind of processes and features with robotics without using simulation is quite challenging. Of course, it can be done. I'm not saying that, but I would. They saw the potential of simulation and OLP in those kind of complex robot systems. So the solution that they implemented in their operations was Visual Components OLP. So they are utilizing that as a platform for the robot offline programming. So basically, they can simulate and create welding programs and handling processes for their robot stations, but they also use the software basically in the first steps of delivering these kind of full solutions. So basically the simulation tools regarding concept design of the layout, feasibility studies and simulation, they are utilizing those together with the customer to try to get the best suitable machinery and layout for their needs and for the end customer needs, but they're also utilizing the virtual commissioning tools. So basically connecting the machines from the simulation world to the actual machines and trying to minimize the errors in the phase where you actually don't have any machinery in the production site. Of course, we're not stopping the cooperation with them for those stages, but we are developing also new tools to further enhance, for example, the connectivity part. So not only connecting to the robots or PLCs, we can also connect to the actual welding equipment. Then the benefits that they got, and these are from one particular project that they made. So of course, if you're making those first concept designs with the end customer, you can get them involved to the actual design, and typically that means that they will get exactly that kind of stations that they need in their production. Minimizing the risks in the sales and commissioning phases, it means that you don't have to make those errors or mistakes in the real life. You can do those with the PC and not utilize the actual production time or such things in the real life. Regarding the commissioning time, these are actual numbers that they achieved. So by utilizing the virtual commissioning, they could do the commissioning of the machinery in the factory acceptance test phase and also at the final acceptance phase 5 to 10 times faster than without the tools. Then of course, if we think about the offline programming itself, they can create those high quality welds for the machines. So basically when they are ramping up the machines at the customer phase, customer site, so they can already start making the production immediately when the commissioning is done. And of course their end customers then using the offline programming for creating more and more programs for their products.
Good. I believe we have another example from you, right?
Yep.
Okay.
So from
Ponsse.
Yep. So this is a little bit different type of example. So the Fronius is working as a system integrator, but Ponsse is working as a manufacturer. So Ponsse is they're a Finnish company, and they are manufacturing for forest harvester machines in Savolax region in Vieremä. It's always important to mention the Savolax region in Finland. Then if we think about the challenges that they were facing, so we started the cooperation with them around 15 years ago already. So at that time they invested in their first robotic welding stations. They started doing the programming with the teach pendant, and of course it is quite time consuming and also complex to make the programs with the teach pendant, and sometimes it caused also delays in their manufacturing process due to the online teaching of the robotic welding station. And what they also noticed that some of the product designs, they were not optimized for automation or robotic welding, and that is quite typical if you have, for example, previously manufactured and welded all the parts with just the manual welding. You don't need to think about reachability of the robot or other things that basically come up to the real life when you have a robotic welding station. And also the last thing is that they didn't stop investing in automation after the first stations, but I think currently they are investing like one robot station per year. So they have already over tens of robot stations, and how to ensure that those new investments actually fit to their production. So basically doing a little bit a pre-study before even thinking about investing in a new stations.
Right, and then maybe you can say a few words about the solution.
Yeah, so they are utilizing currently, and they started utilizing the offline programming tool from Visual Components, of course at that time called Delphi, but currently Visual Components OLP. So they are utilizing that for all of their robotic welding stations. They have different brands in the production, so not only one brand of robots, but they can utilize the same software for all of their stations. What is very nice to see that they are working, or let's say their product design department and also the manufacturing department, they are working together just to make the products more feasible for the robot welding and also designing the welds so that they are easier for the robot to weld. So utilizing the offline programming tool in that sense, it's nice to see that those departments are working together. And then of course, if and when they start planning for the new investments, so they can create those concept layouts by themselves in the beginning, and then basically give the requirements to the robot suppliers that these kind of stations are they need, and they can already start, let's say, doing the first simulation, checking the reachabilities, checking that everything works with this kind of station. And when the robot supplier is chosen, and they get the 3D design of the station, so they can already start making those first welding programs, even though they don't have any station at the production site. So it gives quite good benefits.
Yeah, and you hinted at those benefits, but here again, maybe you can kind of outline those as well. So
yeah, if we think about the programming time compared to the, let's say, first station when they started to teach pendant programming, so with the offline programming they can do it approximately 10 times faster. And of course, with the offline software, there's no production stops with the robotic welding stations. And of course, when they are optimizing the products and optimizing the welds, they are increasing the amount of automation level in their production. And if we think about those new investments, they get a shorter investment cycle, and that is quite critical nowadays because all the lead times for components, robots, welding equipment, they are getting longer and longer, and especially on the COVID times, it's a good thing that you can by yourself even shorter the investment cycle. And of course, the ramp-up time when you actually start the production, if you can reduce that time, it means that you will get the better return on investment on the station, and also production output will be higher in that sense.
Right, exactly. A lot of information here. I think it's time to start bringing everything together. So we're coming towards the end of the webinar here, and we'd like to visit the key learning outcomes here. So what we first looked at is understanding common production challenges faced by our customers, by potential customers, and these are things that we've heard from different sources, and also we got your input to this as well. Then we looked at what is factory simulation and OLP, how does it look in Visual Components, how do you use these tools, and what are their benefits? And lastly, we looked at the different kind of ways you can optimize production volume with simulation and OLP. We looked at the customer cases that hopefully provided you with some more kind of evidence and cases for how these tools can be used. These are just some examples that we saw earlier, but I believe, Jyri, there's a lot more reference stories on our website, right?
Yeah, there's quite many different kind of case stories. So there are examples from system integrators, manufacturers, different kind of companies utilizing the software in different ways, either with the simulation or OLP, or then even both.
Exactly, yeah. Okay, so at this point, I'd like to say thank you very much for everybody who listened. I always appreciate you guys taking interest on this topic, listening to these ideas we have here. And kind of at the end of this presentation, I'd like to leave you with an open question that you can think about after the webinar, which is, what do you think you could do with factory simulation and OLP? Thank you.
Thank you.
Thank you very much, Mikael and Jyri. First question is from David. David is asking, does OLP require Python knowledges? So this is to Jyri, I think.
No, so basically, if you have a robot station and you want to utilize our OLP software for creating the robot programs, so there's no need for any Python coding by yourself. So basically, we create and implement the offline software for you, and then it's just basically showing from the 3D model of the workpiece where the welds or other process paths need to be, and that's it. No Python is needed.
Thank you for the question and for the answer, Jyri. Let me see if anything else. Yes, so question from me or IMI. Can we use simulation for import models from Creo?
So can we use simulation for import models from Creo? So I believe, if I understand the question, is can we import CAD to Visual Components from Creo? Yes, you can import CAD components into Visual Components. That is no problem. On our website, somewhere in the help files, there's a list of all the compatible CAD formats that we support. The list is quite extensive, so I don't think it should be any problem to import CAD files from Creo.
Thank you. Next question. What is the difference between the OLP 4.8 and the Premium 4.8? Does the OLP 4.8 fully include the functions in Premium 4.8? So product-related question.
Okay, so if let's say if you mean Premium 4.8 and if you mean that let's say Visual Components Premium 4.8, so if you don't have the OLP in your product name that you are using, then you don't have the offline programming tools available. But we also have the Visual Components Premium OLP 4.8, so then it has all the features from the simulation side and also all the features from the offline programming side.
Thank you very much. Next question is coming from George. George is asking, how do you ensure fidelity for factory simulations? Is there any way to incorporate an LiDAR, I hope I'm reading this correctly, LiDAR scan or point cloud for validation?
So at least to my knowledge, I haven't been part of this LiDAR scan projects. I might have heard something about it, but to my knowledge, we don't support directly this kind of validation via LiDAR scanning. I think that, again, depends what kind of detail level you're after in the simulation. But if we're talking about a factory level simulation, typically the tools, the way you can locate components, how you can model components is enough for most users. So we don't need this kind of LiDAR scanning for validation. Again, it would be interesting to hear from George exactly what kind of simulations he's after to understand the use case.
Mikael, please correct me if I'm wrong, but isn't it true that we can basically import point clouds if you have like a point cloud of your production hall, for example, and you want to import that to the simulation software?
Yes, correct. Yes, you're right. Yes, I believe so, yeah.
Taking the next one then. So Sagar is asking, does the Visual Components support virtual commissioning? Sorry.
Yes, absolutely. Definitely. We have a whole separate team, connectivity team, who specializes in this. If I go back to one of the slides earlier, so this slide here, so the third black box here, validating control logic, robot programming process. This is all about virtual commissioning. So we have in Visual Components Premium the connectivity features, which allows you to directly connect to a real system. So yes, for example, you can commission your PLCs virtually in Visual Components beforehand.
Thank you, Mikael. The next question from Asbjörn. Have you plans for making statistics exportable for further pure data analysis?
Yes, so it's currently possible to export statistics from Visual Components to a CSV or Excel format. So in that sense, you can do it for pure data analysis. We are also, again, this is down the pipeline. I cannot promise anything, but we are also looking at compatibility with dashboard software. So you can very easily kind of choose the format how you like to view your data. But yes, the statistics is possible to export already from Visual Components.
How will AI affect the programming simulation in the future, or is it already used in the software?
I think that I cannot give a direct answer. We have some plans, but I cannot tell you because I don't want to promise anything that I can hold. I think that AI does have a lot of kind of potential in simulation. For example, in scenario planning. So if we want the AI to go out different scenarios and optimize our production line, for example, this line balancing issue could be done with an AI. So it could be used, for example, in scenario optimization. But at the moment, we do not yet have this, but we have, of course, plans to start investigating this a bit more.
Thank you, Jens. And then a next question is coming from George again. Does Visual Components support scripting in Python, for example?
Yes, exactly. It does, yes. So if you model your own components, we have Python script behavior. So you can, with one click, add a Python script to your component. You can use this for making your own material flow logic, for your own logic, for your components. For example, Güdel used the Python scripting to design their own very smart and specific customized components.
Thank you. Then next question, I think on the OLP side from Andre. Andre is asking, can a laser cutting machine, bending machine, tube laser machine, and welding cells be combined in one layout?
Absolutely, that should be no problem. And I've seen, not with exactly this combination of machines, but I've seen systems with much more different types of machines than just these. So yes, absolutely, you can.
Next question is from Chetan. Chetan is asking, can we calculate load sharing of servo motor with this software?
Not exactly. I haven't myself really done load sharing. I would say that some application of it you probably can, but I don't think it's really what Visual Components is intended for this kind of load analysis. I would say that's more like this. It's potentially a different type of application that Chetan is looking for, but I think it would be worth getting in contact with sales as well in that email to see exactly what his use case is.
Let's see. One question remaining for now. So Shahriamant is asking, can I connect your solution with Process Simulate?
So I believe Process Simulate is another simulation software, if I remember. What we do enable is you can connect data from our software via servers. And if you have also the possibility of doing the same in Process Simulate, so exporting some data to a server and then our software reading that from a server, then yes, it's possible. But again, I'm not exactly sure at what level he wants to connect the two softwares. So that I only use Process Simulate as a manipulator. Well, in the sense, if Visual Components reads data from the server, then technically, yes, it could be. But I haven't myself ever tested this, so I cannot guarantee whether or not that would work.
Next question is coding required to generate real-world scenarios?
No. This is one of the nice parts, is that you don't need to know how to code. And what we do is we, as part of the kind of, if you buy a license, we also tend to sell a 2 or 3 day training which is very customized. So we take into account your use case. We teach all the basics of how to use the software, which allows you to go kind of explore the software yourself and then execute the project. But no coding is needed to create this layout.
Mm-hmm. Then next question, I know even the answer to next question. I see that we can program KUKA robots. What is the other brands that support programming directly from VC 4.8?
You can answer that, Katja.
All the major robot brands, as far as I know. I don't know exactly the number, but
yeah,
I think actually, Jyri, maybe you want to.
Yeah, then let's say on the simulation side, we have almost 1,900 different robots in the e-catalog. But then if we think about an offline programming, so we support 17 different robot brands. Let's say those most typical ones that are used in the industry. So those are that we have post-processor for, and then of course we are increasing the amount all the time. So currently the situation is that we have 17 different brands supported.
Yeah, and I believe we're adding a couple now as well to the next version of Visual Components.
Yeah.
Yeah.
Can Visual Component software be used to assist in scheduling tasks within a manufacturing environment?
That's a pretty generic question. It would be interesting to discuss with Shazad a bit more what he means. I would not use Visual Components as a control kind of center to drive scheduling tasks, but if you wanted to simulate and test the scheduling tasks in Visual Components firsthand to then bring into your actual manufacturing environment, then yes.
The next one is from David. Could we know the saturation of a worker not only for distance traveled, also for amount of loaded part in a specific time?
Yes, so I believe saturation, you mean like utilization rate, but yes, you can definitely find that out. So amount of time it takes to load a part, and also if how kind of worked or how utilized this person is, yes, you can find these out. Or you can simulate these, yeah.
Thank you. The next question from Subin. Do we have the provision to restrict data generation limitation within certain users? For example, if manufacturing being the admin of the simulation software and can restrict product design team to generate production OP report or real-time access to production rate?
So in that case, what I would do is if you have the simulation or if the admin of the simulation software has the simulation file and you would still want to show the simulation to product design team, then what you could do is you could use the Visual Components experience and you could export the simulation to this Visual Components experience where they can only look at the simulation from different angles. So at least that would stop the production design team from generating any kind of data or real-time access to the production rate. But again, it's a bit hard to say definitely because I don't know exactly the use case here.
If I model a layout design, a layout using PM flow components, could I program the logic with a PLC?
Yes, I believe with connectivity, yes, you can use and you can validate the PLC's logic in Visual Components. So you can use connect to the PLC server and then, yes, validate this.
Okay, thank you so much. This is very nice to see so many questions popping up. It means that we have spiked your interest. I thank very much the speakers of today, Mikael and Jyri, and the audience. And on the screen, you can see the email of our sales that can help you with further questions or specifying anything we haven't been able to cover today. So feel free to contact us and also check out our website.
Exactly. Okay, thank you guys for listening and hopefully maybe see you in some customer training or support question or something like this. Thank you.
Thank you very much.